Good morning. Good day, everybody. We will be discussing for this day's lesson, Mathematical Association, which will clarify the concepts of functions and relations. Ang tanong natin, why do we need to understand this? Because when we would like to develop our logical thinking skills, we would have to distinguish types of relations in that one always understands that when we talk about relations in the context of the real world, we either are on a monogamous relation or a polygamous relation if we're talking about the kind of serious marital relations at the level where one is into a form of mutually compensatory form of association. So, taking the cue from the realistic understanding of association, we will also distinguish between functions and relations so that we would be able to have an easier time graphing and visualizing these types of mathematical expressions. Okay. I think you have had your introduction to this in high school, particularly in senior high. Okay, so what are functions? Okay, so if we look at this mapping of set A referred to as input and set B referred to as output, we have elements in the first set consisting of A, B, C, and D, and for the second set, X, Y, and Z. Okay, so in mathematics, a function is a rule that relates a set with another set where every single element in the first set, or set A, which we call input, to one and only one element in set B, illustrated in here as output. So A corresponds to one single element X in the second set, B corresponds to one element in the second set Y, and C corresponds to only one element in the second set, which is also Y, and D in the first set corresponds to Z, one and only one element, which is C in the second set. So this one is a mapping of a function. If we look at the mapping of a relation, then we look at how a first element in the first set, or set A, noted in here as input set, and set B, noted as output set. 0 in the first set corresponds to two elements in the second set, which is 2 and 1. And for the first element 1 in set A, it corresponds to one element, 3 in set B. 2 in set A corresponds to one element in set B, which is 1, and 3 in set A corresponds to 4 in set B. When we look at this will give us a relation, because a relation maps the elements of two sets, sets A and B, such that one element in set A can be associated to more than one element in set B. Doesn't mean that all elements in set A must correspond to more than one element in set B. For as long as there is at least one element in set A which corresponds to more than one element in set B, then that mapping now will be that of a relation. So when we need to understand the differentiation between functions and relations, there are some terms that we need to be familiar with. Okay, so relations would be a set of ordered pairs where the first element corresponds to being in set 1 or set A or input set, and then the second element in the ordered pair belongs to set B or the second set or the output set. All elements of the ordered pair, which will be the first number in the ordered pair, is an element of the domain. The range will be the set of all second number in each ordered pair. Okay, and we have an independent value for the independent variable, which would now be the determinant for the value of the corresponding second element of the ordered pair in the second set or the output set. The dependent value will require knowledge or information of the independent value or the element in the first element in the ordered pair. Okay, so let's look at how one can specify functions and relations. We can either use a formula or a mathematical statement. An example is y is equal to 5x minus 8, or r squared is equal to x squared plus y squared. Or we can use an alternate notation where we use f of x is equal to 4 plus 5x. Okay, x in here is the argument for the function we're calling f. So for, let's say, if f of 1 is given, then that will be equal to, for this example, 4 plus 5, and x being 1 now, this x in the right hand side becomes 1. So 4 plus 5 times 1. F of 0 means the argument for x will be equal to 0. Therefore, we substitute 0 for the value of x on the right hand side. F of negative 5, let's say, becomes f of negative 5 will be equal to 4 plus 5 times negative 5. So that's how we understand this alternate notation for the function. So if we have a function g of m is equal to 3m squared, if m in here is given to be negative 2, then we have g of negative 2 will be equal to 3 times the quantity negative 2 quantity close quantity squared. Okay, so a function or relation can also be specified with a set of ordered pairs. Example will be this set of the first ordered pair is 3b, second is negative 2 and c, third is 5d, and fourth element is 8e. The first element 3, negative 2, 5, and 8 will be elements of the domain of this ordered pair, and B, C, D, and E will be the elements in the range of this set of ordered pairs. So for this second set, we have VQ, first ordered pair, XR, second, WS, third, XT, fourth, and ZS, fifth. So the values or the elements of the domain will be V, X, W, X, Z. But we do not repeat X in the specification of the elements of the domain, but we only will recognize unique elements of the domain. So the elements of the domain for this ordered pair will be V, X, W, and Z. And the elements of the range will be Q, R, S, and T. Okay, we no longer repeat the element S because that has been already specified in the third ordered pair. Okay, or we graph two sets and provide the corresponding mapping, and that will specify for us the set of ordered pairs. Okay, now how do we visualize graphs of functions or relations? We have what we know as the vertical line test to determine if a graph is that of a function or not. What will be the vertical line that we need to draw? We just drop any vertical line through the x-axis at any portion of the graph. When the vertical line meets the graph at one and only one point, then the graph is that of a function. Otherwise, it will be a graph of a relation. So for this example, all the graphs in here, if we drop a vertical line at any point where the graph is, it will meet the graph at some points, 2 points, some points 1, some more than 2 points. So all of these 4 graphs will be graphs of relations. So for this set of graphs, this will be graphs of functions because at any point we drop a vertical line, the vertical line will meet the graph at one and only one point. If we see this specific graph, this curvature means this graph will not meet the y-axis because this tells us that it only approaches the y-axis from the left and from the right, and this one approaches the x-axis from this point, and then in here from the right to the left. So it will not meet the graph at 2 points at the y-axis or when x is equal to 0. So still this will be a graph of a function. So there is another way of specifying functions or sets, because we will be introducing ourselves to sets next meeting. And because ordered pairs are also sets, then we can use the set builder notation. What is this? It is a method of specifying the elements of a set using mathematical expressions. That means using conventional mathematical symbols. So it also specifies the elements of a set that need to satisfy all the given conditions. Okay, so example, if we want to translate the set identified as the set J is the set of real numbers greater than -2 but less than 5. To specify this set J with a set builder notation, we have to specify that the elements of set J are real numbers and must be within the open interval -2, 5. That means the endpoint on the left -2 is not included and the rightmost value of 5 is not also included in the set. So we are saying that this is an open interval, not a closed interval. So the set notation, the set builder notation for that will be J will be equal to the set of all x's such that x, okay, is an element of the real numbers where R stands for real numbers and x is between -2 and 5. Okay, so we also can describe a set by listing the elements. So say we have A is the set consisting of the elements 1, 2, 3, 4 up until 10 is the same as when we specify this set as the set A consisting of all x's such that this bar means such that x is an element of the set of integers symbolized as z, where x is between the closed interval +1 to +10. Okay? Because we are looking at the set of integers, we're only counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because we have the equality sign in here, we include 10 in the set and also 1 in the set. So the endpoints are included. Okay, so to recall, we need to recall the symbols for sets of numbers. We use N for natural numbers, Z for the set of integers, Q for the set of rational numbers, R for the set of real numbers, P for the set of irrational numbers, and we have the imaginary numbers and the complex numbers. So for the set of natural numbers, we start with 0, 1, 2, 3, and so on. For Z, the set of integers, we go from the negative integers to the positive integers, including 0. The set of rational numbers will be all numbers that can be expressed as a ratio or quotient of two integers. So that will be the set of rational numbers. So the set of irrational numbers will be those numbers which cannot be expressed as quotient of two integers. So the set of real numbers consists of all numbers in the number line. Okay, and P will be the set of irrational numbers. Okay, so now recalling all those conventional symbols for a set builder notation, suppose we would like to specify set A using the list of elements as we have given out in the previous example. The same set can be specified using the set builder notation as A will be the set of all x's such that x is an element of the set of integers such that x is between 1 and 10. But if we would like to specify that these are all positive, we can provide it should actually be let's see if it works. Okay, so the positive in here will tell us that we are looking at the positive integers. Okay, so this will be a refinement of the previous example we cited. Suppose again we have set B specified as the set of all y such that y is in the set of integers such that y is greater than 7. Okay, so greater than 7 means the set B will consist of 8, 9, 10, 11, 12, and so on. Suppose we want G to be the set of all W such that W is an element of the real numbers where W is between -2 to +3. So we can also specify that as G is within the open interval -2 to 3. Okay, so this is where we end our lesson on the functions and relations, just so you can be introduced to this world where we can always have ordered pairs or parts of the number line. When we look at ordered pairs, that means now that we will be working with the XY plane, or that we will be working with the two-dimensional plane. The two-dimensional plane has four quadrants. First quadrant will be both positive, XY positive. Second quadrant, X is positive, Y is negative. Third quadrant, both negative, X, Y will be both negative. And the fourth quadrant will be X is negative and Y axis will be the positive axis. So we go clockwise. So this is where we will end. Our next discussion will be given out in audio form so that we could cut up our lessons in small bites. Otherwise, GIF, the Google form, the Google Suite will not run through the antivirus scanning if we over record or record our lesson longer than we should. Okay, to safeguard the laptop or the computer system, we will be managing the length of our audio recording into small bites. Thank you very much for your attention. If you have questions, please let me know and we will clarify those. Thank you and have a good day.